Welcome back to the VeraGrid Feature Spotlight series. In this episode, we're moving beyond static snapshots to explore time series analysis. A single power flow result is like a photo. It tells you what the grid looks like at one specific moment. That's a vital foundation, but what we usually need is the movie, how voltages, loading, and dispatch evolve as demand shifts and renewable generation moves throughout the day, the week, or the year. VeraGrid handles this with a clean separation between the physical network model and time-dependent inputs. The network infrastructure is defined once in a multi-circuit object and stays unchanged during execution. Then, time-varying inputs like load and generation forecasts are introduced as index profiles attached to the relevant elements. Each time index represents a new operating condition applied to the exact same physical grid model, which keeps studies reliable and easy to reproduce. Under the hood, VeraGrid compiles each time step into a numerical circuit, a solver-ready representation containing the matrices, injection vectors, and indices required for the simulation. At first glance, this extra computational step might seem redundant, but it is built from fast copy operations and plays an important role in performance. By reorganizing the object-oriented multi-circuit into an array-oriented numerical structure, VeraGrid aligns the data in memory and makes numerical calculations much more efficient. Just as importantly, simulation results never modify your original inputs, so your dataset stays clean and your workflows remain replicable, which is not always the case for other open source or commercial tools. Let's see how to work with time series in the IEEE 14 bus system. To create the time series, go to the database and click the Create Time Series button. Here we can choose the amount of time steps, start date, and the unit length of each time step, which can be whichever you require for your use. To fill the data, we have a few options. We can fill the data manually, although this is not recommended. We can also import the data from multiple snapshot models of VeraGrid compatible models, or import the profiles as data frames through code. Finally, we can import from an existing Excel spreadsheet of generation and load profiles. Let's take a look at how this works with a generator active power profile for solar and wind plants. When loading profiles, we first check that our input file has the correct amount of rows. If this condition is not met, VeraGrid will return an error on input. We selected some preloaded profiles that we have ready and match them individually to the plants by selecting a profile and double-clicking on the plant to assign it to. We also have options to set unassigned profiles to 0 and normalize the entry values based on the plant rated power. Once the profiles are loaded, we also have the option to set these profiles to non-dispatchable, which means they will not be controlled by the OPF. Now that we've imported, we can easily visualize the imported profiles by plotting them and can zoom in on zones of interest. Now, let's repeat the process for the load active and reactive power. Here, we can explore some other import options. If our VeraGrid load names and profile names match, we can match directly by name. We can also randomly assign profile to objects, assign one profile to all objects, or assign one profile to a selection of objects. Once we have the required profiles defined, we can activate the time series simulations using the icon in the toolbar, and also edit the start and end time of the time series. Let us now simulate a linear OPF over this time frame. Once this OPF completes, we can then directly pass the dispatch from the OPF to the power flow and contingency analysis. And now we can run these as well. Once our simulations are completed, we can now click on any of the elements in the grid and plot the relevant profiles. For branch elements, the branch loading will appear, and for bus elements, the voltage will appear. Let's take a look, for example, at the loading variation and cumulative density function of two lines and the voltage variation at two different nodes. As in the snapshot cases, we can also navigate to the Results tab and plot results of individual simulations from there as well. Of course, anything we can do with the GUI can also be replicated through code. In the example shown below, we are first creating all the n-1 branch contingencies, then running the OPF, power flow, and contingencies through code. Finally, we use the simulation results to highlight the four most loaded branches under contingency conditions and the three nodes with largest voltage deviation and their loading CDF. That wraps up this feature spotlight. If you have any questions or run into something you'd like clarified, feel free to leave a comment below, check out our documentation, or reach out to us directly on Discord. We're always happy to help. We'd also love to see what you build with VeraGrid, so don't hesitate to share your projects or results with us through the contact links in the description. And finally, if there's a feature you'd like to see added, consider contributing to the project. Your ideas and feedback play a big role in shaping the future of VeraGrid. Thanks for watching, and see you in the next video.